Now that you've had a chance to work on some of the activities related to the division algorithm, we're going to take a closer look at the division algorithm and in particular, look at its proof. So first, we're going to review the statement of the division algorithm. We're going to add in a uniqueness element to the statement that will become clear when we get there. Then we're going to review the well-ordering principle, which remember was a new axiom that we added to the integers. And then we're going to prove the existence part of the theorem. The uniqueness part of the theorem will be discussed in the next video. All right, so just recall that in the old days we were motivated by what happens when we divide b by a and don't get an integer as a result. Well, the way we were looking at it was that you get a quotient q, a remainder r, and the way that those two things are related is that b is equal to aq plus r. And one of the things we discussed is that if you didn't have any particular expectations of what your remainder is, you could have a lot of different combinations of a quotient q and a remainder r. However, we were only interested in remainders that were, first of all, non-negative and that were smaller than a, smaller than the number we were dividing by. So that led us to the following conjecture. Well, it's actually a theorem, we'll call it that. Let a and b be integers where a is a positive number. Then there exist integers q and r such that b is equal to aq plus r. In other words, q is a quotient, r is a remainder. And r is between 0 and a minus 1. So non-negative and smaller than a. And then also, and you might have to think back to your experience in doing division, there was never a case when you were doing a division problem and got one quotient and remainder, and that someone next to you who may have been doing the problem slightly differently but correctly got a different quotient and remainder, right? As long as the remainder was between 0 and a minus 1, you always got the same quotient, you always got the same remainder. Well, that's not a coincidence. That actually happens all the time. So that tells us that our quotient q and our remainder r are unique. And so we can add that to the theorem. So all I did was take the theorem and replace it with there exist unique q and r in the integers such that b is equal to aq plus r and r is between 0 and a minus 1. Which means that there is precisely one quotient and precisely one remainder that make the remainder be between 0 and a minus 1. The other thing that I want you to recall is the well-ordering principle. And this was our new axiom on integers that distinguishes it from other number systems like the rational numbers and the real numbers. So suppose you have a non-empty set of integers that does not contain any negative integers. Then our conclusion is that S has a smallest element. All right. So here's our theorem. I'm just rewriting the theorem so you can see it. To prove that theorem, we actually need to prove two things. We need to prove that the quotient and the remainder exist. In other words, there is a remainder between 0 and a minus 1 and a quotient that goes along with it. And then we also have to prove that the quotient and remainder that satisfy those conditions are unique. Okay, so we're going to deal with one of those here, the fact that they exist. The uniqueness part we're going to deal with in the next video. So here is how we're going to approach the existence part of the proof. Well, remember, we want the smallest remainder possible that is also non-negative. And if you see smallest and non-negative, and oh yeah, by the way, it's an integer, all three of those things together, then we're really talking about the well-ordering principle, right? The well-ordering principle is a perfect fit for that type of problem. So what we're going to do is we're going to look at all the remainders that are negative, and then out of all those remainders, we're going to choose the smallest one using the well-ordering principle. So remember, this is the equation that tells us the relationship between a quotient q and a remainder r, b equals aq plus r. So what does a remainder look like? Well, one way of understanding that is to take that equation, solve for r. Remainders are things like that r that are of the form b minus aq. So remember, b and a are given. I'm dividing b by a. Q can literally be any integer. So if I want to find all the possible remainders, I just plug in all the values of q, and those will give me all the possible remainders. But again, remember, we only want the remainders that are non-negative. So we're going to define our S to be the set of all x in the whole numbers. And remember, the whole numbers are really, those are all the non-negative integers, such that x has the form of a remainder. X is equal to b minus aq for some integer q. So what S is, what S is the set of all remainders that are non-negative, which is exactly what we wanted. Now, the well-ordering principle will imply that S has the smallest element as long as, right, there are always conditions. A couple things happen. First of all, S can't be the empty set. If S is the empty set, then there's nothing in there, let alone the smallest element. And the second thing is that S does not have any negative numbers. And that one is not going to be a problem at all. That's going to follow directly from how we defined S. All right, so here is, again, our definition of what S is, and we want to show that S is non-empty. And again, non-empty just means there's an element in there. So if we can actually find a single element in S, we don't have to find all of them, we just have to find one, that will imply that it's non-empty. Well, let's see. So we want to find an element in there that has the form b minus aq. We have no choice over what b and a is. And so all we really have to do is choose a q, and that will give us an example of an element in S, as long as the remainder it gives us, the b minus aq, is non-negative. So let's see. Well, probably the easiest q to choose is q equals 0. So we're going to choose q equals 0, throw it in there, see if it gives us anything useful. Well, if we do that, q equals 0 gives us x equals b minus a times 0. The a times 0 just disappears and we get b, which tells us that b is a remainder. But the question is it a non-negative remainder? Because if it's a negative remainder, then it's not going to be an S. Well, so if b happens to be a non-negative number, then b is a remainder that's non-negative. It's an element of S, right? So, well, okay, so that takes care of all the possibilities for b being a non-negative integer. That's actually pretty good. That takes care of like, what, half, if you want to think of it that way, right? So now let's see what happens if b is a negative number. So if b is a negative number, we still have to find an element in there. We're not going to find it by letting q equal 0, because that'll give us b, which is a negative number. We have to choose a different q. So you folks played around with that in the activities last time, and this will be very consistent with the work you did there, probably. We're going to choose q to be b. Now, b is an integer, and remember that q doesn't have to be a positive integer. It could be any integer. It could be any integer. It just has to make b minus aq a non-negative number. Well, let's see if it makes b minus aq a non-negative number. So if we plug in q equals b, we get b minus ab. Well, that's pretty convenient. We have a common factor of b in both of those. So if we factor out that b, we get 1 minus a times b. All right, so let's see if we can figure out whether that number is negative or not. Let's see. Well, all we know about a is that it is greater than 0. Oh, and that it's an integer, right? So since it's an integer and it's greater than 0, it has to be at least 1. And then if I subtract a from both sides and sort of flip that inequality around, that tells us that 1 minus a is less than or equal to 0. I mean, literally it tells us that 0 is greater than or equal to 1 minus a, but if we flip that around, that gives us 1 minus a is less than or equal to 0. So let's see what that tells us about our x, right? Our x, remember, is 1 minus a times b. 1 minus a is a non-positive number, right? B we know is a negative number. So let's see. So non-positive means either 0 or negative, right? If it's 0, then 0 times negative is 0. And if it's negative, negative times negative is positive. So that non-positive times negative is either going to be 0 or a positive number. That means it's going to be a non-negative number, which tells us that x is greater than or equal to 0. So we already knew that x was a remainder. It was b minus a times q. Our q in that case was b, right? And now we know that it's a remainder that was greater than or equal to 0. That means that x is an S. So S is non-empty, right? So what this tells us is if b is greater than or equal to 0, then x equals b is an S. If b is less than 0, then x equals b minus a times b is also an S. So in either case, S has an element in there. And that tells us that S is a non-empty set. Now remember, we also defined S so that it only has whole numbers, right? X had to be a whole number, which means that it doesn't have any negative numbers. So we've got a set of integers that is non-empty and doesn't have any negative integers. That means by the well-ordering principle that it has a smallest element, which we are going to call wink, wink, nudge, nudge. We're going to call that R, right? All right, so we worked hard to get that R, but let's just sort of summarize what we know about R before we start jumping in. First of all, since R is in S, R has to be of the form b minus aq for some integer q, right? That's just the definition of what S is, and R is in there, right? But remember, also R is in there means that R is greater than or equal to 0 because we only allow remainders in S that are non-negative. And then the third thing we know, since R is the smallest element of S, that means any other element in S is bigger than R. So if we happen to find another element of S that is not R, it is going to be bigger. So R is smaller than that element, or that element is bigger than R, however you want to look at it. All right, so what do we have to prove? Well, remember, we have to prove that B is equal to AQ plus R. That was just part of the theorem, right? And we have to show that R is between 0 and A minus 1. Well, that first one shouldn't be too bad, right? Because we know that R is equal to B minus AQ. All we have to do is solve for B in that equation. We get B equals AQ plus R. That was the first thing we had to prove. We know R is greater than or equal to 0, right? Because that's by definition, and that's also that second bullet point that we have up there, right? Which means that, well, if we want to turn that around, that 0 is less than or equal to R. So the only thing in that whole theorem that we haven't proven is we haven't proven that R is less than or equal to A minus 1. Once we prove that, we are done. All right, so that's just one thing left we have to do. All right, we can do it. We can do it. All right, so we're going to prove that R is less than or equal to A minus 1 by contradiction. All right, so we're going to assume that it's not true that R is less than or equal to A minus 1, which means that R is greater than A minus 1. But remember, R is an integer, A is an integer, 1 is an integer. They're all integers up there, right? So if R is an integer greater than another integer, that means it has to be at least as big as the next integer. So A minus 1 is an integer that R is bigger than. That means it has to be at least as big as A, which is the next one up. And if we subtract A from both sides, that tells us that R minus A is greater than or equal to 0. And that fact's going to be important to us, so keep an eye on that one. All right, so remember, we know that R is equal to B minus AQ, where Q is an integer. If I subtract A from both sides to make it look like R minus A, then that's what I get. I get R minus A is equal to B minus AQ minus A. And if you look at the last two terms on the right-hand side, you will notice that they both have a common factor of A. So I'm going to go ahead and factor in A, not out of the whole thing, because that B doesn't have it, but out of the last two terms. And so we get B minus the quantity Q plus 1 times A. And now that's looking a lot like an element of S, right? Because Q is an integer, 1 is an integer. That tells us that Q plus 1 is an integer. And again, I have that R minus A is equal to B minus an integer times A. That's almost all of what it means to be an S. And then we also know, remember, 2 lines up, that R minus A is greater than or equal to 0. So if we put all three of those facts together, Q plus 1 is an integer. R minus A is equal to B minus Q plus 1 times A, so it's equal to B minus an integer times A, and R minus A greater than or equal to 0. That is exactly what it means for R minus A to be an element of S. So R minus A is an S. However, we also know that R minus A is less than R. Remember, A is a positive number. If I take R and subtract a positive number, I get a smaller number than R. But R is the smallest element in S. So I got R minus A is an element of S that's smaller than the smallest element of S. That is a contradiction, which implies that R is less than or equal to A minus 1. All right, well, that was a lot of work on that proof. Once you've digested this one, I suggest you go on to the next video. That's the uniqueness part of the division algorithm, and I'll see you there.